have a function, and you have derived a formula for the inverse, and you've proved that it is the inverse by showing that the composition of the function and its inverse formula and vice versa both work back to the identity, that automatically gives you injectivity. You don't need a separate proof of injectivity, technically speaking, because this is like, this is a theorem. Like, okay, so f is inverse is a function. The proof for part B is really very silly. If we have f inverse as a function, right, and we have f of A is equal to f of B, then f inverse of f of A is equal to f inverse of f of B, which tells me that A is equal to B, which tells me that f is injective, all right? So that's the proof of part B. We already proved that in part A, technically speaking, right? The reason I've written that off separately as a separate result is just to emphasize to you guys this is something we know. If we have an inverse formula for our function, and we have actually proved that it's the inverse formula, right? Not just claimed that it's the inverse formula, then we've already proved one-to-one. Like over here, in example 4, if we continued this thought and we actually proved that when I plug in 3 plus the cube root of y into the x minus 3 formula, and that works back to just y, and if I also prove that when I plug in x minus 3 cubed into this formula, and it works back out to just x, when I've actually showed that h composed with h inverse and h inverse composed with h is in fact the identity in R, that point I have already proved that h is a one-to-one map. And by the way, also that h inverse is a one-to-one map. I don't know if you noticed this or not, but a function is its own inverse, right? Like, that's another kind of silly theorem, Theorem. If f inverse exists for f from A to B, then f inverse is equal to f, right? We could prove that. All right. So corollary to this theorem, I'm going to erase this if you guys don't mind. Actually, I'll work over here. So a corollary to this theorem is that if we take two bijections and we compose them, guess what? We get another bijection. So corollary. If f compose, good grief, if f from A to B and G from B to C are bijections, then let's see here. I always have trouble. I think G composed with F is a mapping from where to where? A to what? A to C, right? Is a bijection. I said proof left to the reader. That sounds like a threat of a homework problem. So to give a proper proof of this, maybe you should show that the composition of injective functions is injective, right? And the composition of surjective functions is surjective, yeah? All right, well, my next theorem seems to say more of the same thing. I just changed the words a bit. Sometimes I think there's some things that have gotten doubled up perhaps when I re-edited these notes. But let's see here. Here's a theorem. Oh, I'm going to stop with the theorems. I don't want to hurry through any. I'd like to prove some of these theorems maybe next time. So let's actually take the last 5 minutes of class to look at problem 2 on the quiz. Yeah? So this is finally a non-trivial calculation today. Example 5. Here we're given f of x equals to the sinh of x, right? And you're supposed to find a formula for the inverse function in terms of logs and algebraic functions, all right? So, first of all, let me encourage you that this function is in fact a bijection. Why is that true? Well, notice that df dx is equal to cosh x, which by the way is greater than or equal to 1. So this function's strictly increasing on the reals, which means it can never double back on itself. It's going to pass the horizontal line test actually. So the inverse hyperbolic sign exists. We can be confident of that. So let's find it. So what we're looking at is y equals to the sinh of x. To find the formula for the inverse function, we simply solve for x. Now you might have been taught that you have to switch x and y to solve for that first in your pre-calculus class. That's because whoever taught you doesn't believe that you can think about a function of y. I no longer think that. I think we can think about a function of y. It's not a big deal. But this thing where they flip the x and the y at the start of the calculation, that's just so you find the inverse function of x, right? But we think about functions of y in here just the same. So this is 1/2 e to the x plus e to the minus x. All right, that's the definition of hyperbolic sign. Multiply 2 to the other side, and we've got 2y is equal to e to the x. Oh, was that a plus? No, that was a minus. Minus e to the minus x. Which, if you tilt your head and squint, you can see that that's actually e to the x minus 2y minus e to the minus x equals to 0. All right, nothing big there. Next move, multiply the equation by e to the x. This gives me e to the x squared minus 2y e to the x minus 1 equal to 0. The reason I did that is in order to see that it's quadratic in e to the x. And I can complete the square. You see, this is e to the x minus y, quantity squared. Right, if you square this, we get e to the x squared, we get the minus 2y e to the x, and we also get a plus y squared, right? So to be fair, I must subtract y squared. Which is to tell me I have e to the x minus y quantity squared is equal to y squared plus 1. Which tells me that e to the x minus y is equal to the square root of y squared plus 1. I can tell that it's the square root over here because this is, I don't need the minus here because this is manifestly, maybe I do need the minus. A second here. Plus or minus? I guess I do need the plus or minus. Square root both sides, yeah. So that gives me e to the x is equal to y plus or minus the square root of y squared plus 1. Which then, taking the natural log of both sides, gives me that x is the natural log of y plus or minus the square root of y squared plus 1. Search your heart. Find that only one of those is real, because we can't take the log of a negative number, yes? So definitely the minus is a bad move because y squared plus 1 is manifestly larger in magnitude. The square root of y squared plus 1 is larger in magnitude than y, and as such the minus is intolerable from the perspective of real analysis, right? It's going to give us log of a negative number if we take the minus here because this is larger in magnitude than that. So therefore, the inverse hyperbolic sign of y is equal to the natural log of y plus the square root of y squared plus 1. There you go. That was the answer to your second quiz problem. So How many of you would have got this today? No chance. I don't know. If you had a really strong pre-calculus teacher, you might have seen this before. Yeah. The formula for inverse hyperbolic cosine and the formula for inverse hyperbolic tangent can also be derived in a similar fashion. Inverse hyperbolic tangent's a little bit easier. Inverse hyperbolic cosine requires a restriction of the domain because inverse hyperbolic cosine is an even function. It's not one-to-one, so you have to restrict the domain to be like positive inputs to get an inverse, which is what's typically done. Anyway, we'll do more of this next time. If you came late, you missed the April Fool's quiz, so oh well. Maybe next time.